Okay, so a quick review. We are partway through our second pass through all of the material of the course. Remember that our three big topics are what is a fluid, fluid statics, and fluid dynamics. And so the first time through our what is a fluid topic, we basically talked about this one relationship for a Newtonian fluid that says that the shear stress is proportional to the velocity gradient by this factor called mu, which is the fluid viscosity, and that's a property like density and things like that. The second time through, we got a little fancier with that, where we started looking at differential elements, and so we found differential forces by multiplying that shear by a differential area. You could turn that into a differential torque if you wanted to multiply that differential force by some distance that it acts over. We also looked at differential mass flow rate. So this is the mass flow rate through a tiny area, which is just rho VA, but times a tiny area, this dA, instead of a big one. And also we looked at the differential mass, which you can get from multiplying the density times a differential volume. Remember that V with a line through it is just to let you know it's a capital. Next we moved on to fluid statics. This is the science of fluids that don't move. The first time through we discovered that in a gravity field you can always take the pressure at the top, and as you move down in the fluid by a distance h, you can add rho gh to get the pressure at the bottom. And so you can do this between any 2 points vertically in a field. Just remember that h here is the distance that you've moved downward and not necessarily a signed coordinate system. We used that principle our second time through on things like manometers to measure a pressure, right? We could measure the difference between 2 and 1 by looking at h if we set up a U-tube or something like that. And then we looked at buoyancy, which is basically the force that causes things to want to float. And so here what we saw was that the buoyancy force experienced by a body, the force up, is equal to the weight of the displaced fluid. And so you could calculate the mass of displaced fluid by using density of fluid times the volume of the submerged object, and then multiply that by gravity to get the weight, and that would give you the buoyancy force pushing upwards. Next we looked at fluid dynamics. We looked at the Bernoulli equation here, which says that the pressure, velocity, and elevation are related for a fluid along a streamline. And so following these assumptions, what that lets us do is we can relate 2 points on a streamline and start to find out all kinds of interesting things. If you move that to an internal flow, such as flow through a pipe, you can divide by g, which puts each one of these terms in units of length. We call that head. And so this would be the total head at station 1, the total head at station 2, and they're equal to each other with a couple of differences. The first is the head loss, which is caused by friction, and the second is pump head, which is something that adds work like a pump. And so we can get from station 1 to station 2 despite the head loss by adding the pump head. So what's this head loss? Well, it's the pressure drop caused by friction. We can find that theoretically, do a little bit of algebra here, and discover that it's equal to this relationship here, which says that the shear stress multiplied by 4L over D gives you the pressure drop caused by friction. But that's inconvenient because this goes all the way back to needing to use the mu to u dy and all that business and needing velocity profiles. What a hassle. And so we've correlated it for you on a thing called the Moody Diagram. This friction factor F can be used to calculate it. And so we go and we look up the friction factor as a function of two things, the Reynolds number and the relative roughness of our material. And you plug it into this definition, and that also will give you the pressure drop. The other correlation that we like to use for external flows here is drag and lift coefficient. So an external flow, remember, is something that is submerged as opposed to a tube. And so first off, you can look at a drag coefficient. It just takes the drag force and normalizes it by this 1/2 rho u squared a. And so we can look up these drag coefficients, and ditto for lift coefficients, for all kinds of shapes, and really quickly get what the lift and drag force would be at a given condition.